was to anticipate what the bar graph would look like if we flipped a coin 6 times instead of 4 for each trial. So you would have the possibility of getting up to 6 heads, okay? And we would imagine that it would still have that same bell type shape, that it would be symmetric. Okay, it's probably not going to be perfect. And at this point in our mathematical careers, I don't know that we have the level of sophistication to actually anticipate a frequency out of those trials, but like the shape, it's a sketch, right? So it doesn't have to be like totally detailed. Any questions about this? Okay, flip. All right, we are going to look at part 2, which is modeling a data distribution with the normal curve. We already watched, oops, I guess we were not supposed to do that at the very beginning, but we already did this. We watched the first 2 minutes and 30 seconds of the Galton board video. Do we need to see it again? Okay, we got it? Okay, cool. When a histogram of a data distribution has a bell shape, the distribution can often be modeled by a normal curve, which is a bell-shaped continuous function that looks like this. Okay, notice that I can do the vertical line test on it, and it only, here, I'll even drag it around. Okay, here's my vertical line, and I can drag it around, and it only ever touches my function in one place at a time. That means that for every input, there is exactly one output, right? Okay. Notice that it's continuous. There's no breaks in it. There's not any jumps in it. Okay, you don't have to lift up your pencil to trace it. Okay, the properties for a normal curve make it a useful model for data distributions. In an approximately normal distribution, the percentages of data that fall within intervals determined by the mean and standard deviation, sigma, are as follows. Okay, this is important. Okay, so we know that sigma is our standard deviation, right? Okay, so here is our mean. So this is your x with a bar. So let's just say, like, for example, that our mean was 10. Okay, just for instance. Let's say it was 10. What do you want to pick for our standard deviation? Just as an example to wrap our heads around this. 2? 2's nice. Okay, so let's just say that our little sigma was 2. So if I add 1 sigma, that would be 1, 2, which is a 2, right? So this would be at 12. Okay, if I take away a sigma, which is a 2, in this case that I just made up off the top of my head, I'd be at 8. Okay, that means that approximately 68% of our data is going to fall between 8 and 12, which is the area region between within one standard deviation of 10. Does that make sense to everybody? Okay, let's bring it out. We've still got our little sigma is 2. Now, if we go out to twice sigma, so 2 times sigma would be 2 times 2 in this case, because we said sigma was 2. That would be 4. So here's my 10. This would be if I add 4, that would be at 14. And this would be if I subtract 4, which would be at 6. So I'm taking away 2 sigmas. Okay, 95% of our data is going to be within 2 standard deviations of our mean. 95%. That's almost everybody. That's kind of cool, huh? Okay, last one. 3 sigmas. Okay, so here's our mean still. Our mean is still 10. Okay, 3 sigmas in this case would be 3 times 2, which is 6. So if I take 10 and add 6, I'm out here at 16. And if I subtract 6, I'm at 4. So just because we're subtracting sigmas doesn't mean that we're going to be at a negative value. Does that make sense to everybody? Okay. 99.7% of our data falls within 3 standard deviations of our mean. Very nearly everybody. Okay, so this rule has an important name, and I'm not really sure how to spell it, if I'm honest. Maybe it's down here. Oh, no, it's not. Okay, it's called the empirical rule. And I don't know if it starts with an E or an I. How many times do you have to spell it? Okay, we're just going to look it up real quick. Could happen to anybody, right? All right. Empirical rule. Okay, also known as the 68, 95, 99.6 rule. Oh, is that supposed to be a 7? Okay, using the normal curve as a model for data allows us to predict the likelihood of specific data values or intervals occurring. Everybody okay with that? Okay. Okay. Naturally occurring phenomena fall into an approximately normal distribution, including heights of people in a population. Here is a histogram which shows the distribution of baby birth weights in the United Kingdom. Okay, so here I have birth weights in the UK. What do we notice about the histogram and its relationship to the normal curve drawn on it? It is incredibly close, but is it perfect? No, sometimes it's above and sometimes it's below, but it is approximately normal. Okay, in the data shown, the mean weight of a newborn baby is 3.39 kilograms. Okay, let's draw that on here. I like to do the mean in red. I don't know why. 3. It's okay. This is just fun for the video. Great. Okay, 3.39. So a little bit less than 3.5. Did I do that right? That looks pretty good. Okay, not bad. Okay, and our standard deviation is 0.55. So this was 3.39. Okay, so what would we get if we added 0.55 to our 3.39? Try it on your calculator. 3.39 plus 1 standard deviation plus 0.55. What was it? 3.94? Okay, so that one I'm going to do in orange. Okay, so this is plus sigma, and it's at 3.39. 9.4 you said?
Yeah.
Okay, what if we subtract from 3.39 the 0.55? 2.84. I'm trying to get my things in the right spot. Okay, so this was minus 1 sigma, and it's at 2.84. Okay, what percent of our data falls in that range? 68%. According to the empirical rule, it's 68% of our data falls in there. Okay, now they're going to tell us some more information. How many newborn babies are represented in this sample? How many newborn babies? Okay, right here, guys. Yeah, 3,226 babies. Okay, and we want to know how many of them are in this range. So if I know that 68% of the newborn babies fall within 1 standard deviation, how would I find that using the number of babies? Yes. 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 Okay, so first we got to convert the 68 back into a decimal, right? So 68%. Okay, we can move the decimal point over to the left and we get 0.68. So we take our number of babies times 0.68 and we get, can you give me 2 decimal places? What was it? 2,000?
193.68.
Okay, just say the numbers and say them out because I'm old and my ears don't work. 2193.
2193.68.
Thank you. 0.68 babies. Okay, and these babies are within 1 standard deviation of the mean. Within, oh shoot. Oh my gosh. 1 standard deviation of the mean. Okay, so let's just go through the strategy. Okay, they gave us the mean. We added 1 standard deviation to it. We subtracted 1 standard deviation from it. That gives us the range. Okay, we know that 68% of the babies fall in that category. So we can take the number of babies times the 0.68, and that gives us the number of babies in that area under the curve, approximately. Questions? Easy enough, right? Okay. All right, about how many newborns from the study would you expect to have birth weights within 2 standard deviations of the mean? 95%. Okay, does that tell you how many or does that tell you what percent? Okay, so we have a little bit, 95% will help us get there, but we have a little bit more work to do. So 95% of how many babies? 3,000? What was it? 3,200. Sorry. 3,226. Okay. Okay, so I have to convert my percent into a decimal, that would be 0.95, and multiply that with the total number of babies. I guess I could get my calculator too. I'll show you in a second. Okay, I got 3,064.7 newborns. Have I been saying babies this whole time and I should have said newborns? Oh my gosh, we're not going back. We're just, okay, video people, I'm sorry. Just got to change all the babies to newborns. It's my bad. Okay, about how many newborns from the study would you expect to have birth weights within 3 standard deviations of the mean? Okay, so this time we got to do 99 point, was it 7? 7%. So we still have to move the decimal point 2 places to the left. So this time we're going to multiply by 0.997. I got 3,216.322 newborns. Is that what you guys got? Okay, good. Okay. If these data are an indication of birth weights in general, would you expect many newborns to have a birth weight of 5.5 kilograms or 10 pounds? Why or why not? Okay, 5.5 kilograms. Let's see where that is. Let's do that one in green. 5.5 is all the way here. 5.5. So, okay, why not?
Because after 5, the baby stop.
Well, I mean, there's like a, you're not really wrong, but there's a better way to say it. Okay, so can we imagine that the second standard deviation is about here? Okay, and then the third is like here. So how many standard deviations away is that? Like 4. So next to no babies are out there, newborns. Right? So go ahead and put that in your own words. I mean, at 3 standard deviations, it's already almost 100% of the data is like represented at 3 standard deviations. So if we're talking about going out to 4, it's like a tiny percent of babies that would be that heavy. This is a massive newborn. Okay. Was that the end of that page? Was that the end of the thing?
Yes.
All right, guys, we have like a full half an hour of work time. Okay. Okay, we would say very few newborns would have this weight. Would weigh 5.5 kilograms because 5.5 kilograms is more than 4 standard deviations away from the mean. Okay, and so by the empirical rule is saying that only a fraction of a percent of data is farther than 3 standard deviations away. So if we're at 4 standard deviations, it's like very, very unlikely. Not impossible, but extremely unlikely. Okay, that's it.